Okay, so in a previous video, we looked at refraction in sort of a conceptual way. Why does refraction happen? How does it happen? Kind of those ideas of going from one medium to another and light bending and whether it bends towards the normal or away from the normal. So we looked at all of refraction conceptually. We can also look at refraction mathematically. We can define specifically how much a light ray will bend as it goes from one medium to another. And that's done through an equation known as Snell's Law, a relationship known as Snell's Law. And Snell's Law tells us that the index of refraction of one medium times the sine of the angle for that medium, so the angle at which the light ray hits the boundary, is equal to the index of refraction of the second medium times the sine of the angle for that medium. So let's just redefine what these things are so that we can clearly articulate what is represented here and then use it in an example. So let's imagine that we have a boundary between two mediums, and we'll say we have air and plexiglass. And so we know that the ray of light that's in the medium incident on that boundary, and in our example we're going to use air. So here's our ray of light incident on that boundary. This is what we call the incident ray. And it hits at this point of incidence. The angle at which it hits that boundary is taken, remember, relative to the normal. So this is our incident ray, the ray relative to the normal. And we draw that normal at the point of incidence to that boundary, the normal to the boundary at the point of incidence. Now, a refracted ray, so as we go from air to plexiglass, we're going from a low index of refraction to a higher index of refraction. We bend towards the normal. So if this were our no bending case, no medium case, we would bend towards the normal, and perhaps we'd have something like that. This is the refracted ray in the medium of the plexiglass. And again, the angle is relative of refraction. I put 2 there from thinking of my equation. The angle of refraction is relative to that normal. All right, so just a reminder of some of that terminology. So now let's use Snell's law to look at how the angles actually manifest. So we've talked about and we conceptualized that if I go from a low index to a high index, I'm going to bend towards the normal. Let's see if the equation works for that. How is my angle of incidence compared to my angle of refraction? We would expect that the angle of incidence is greater than the angle of refraction when we go from low to high. So let's use this as our example and just test that idea. All right. Air has an index of refraction of 1.0029. Plexiglass has an index of refraction of about 1.46. So there's my 2 indices of refraction for air and plexiglass. We will have air be our N1, and we'll have plexiglass as our N2. And what we want to know is if I know the angle of incidence, what will my angle of refraction be in plexiglass? So let's say that our angle of incidence in this example is 25 degrees. All right, so we're interested in determining the angle of refraction. We're going to use Snell's law to do it. So Snell's law tells us that the angle of incidence in one medium, we'll say air, times the sine of that angle, we'll say 25. So the index of refraction, I think I said that wrong, the index of refraction times the sine of the angle is equal to the index of refraction of the second medium times the sine of its angle. All right, so I'm interested in knowing what is the refracted angle. So that is theta 2. That's what I want to know. So let's solve for theta 2. We have N1 sine of theta 1 all over N2 is going to give me the sine of theta 2 And then we can take the inverse sign to get that. But before we do that, let's look at this relationship, and then we'll take the inverse sign. So, all right, so N1, 1.00029 times the sine of 25 degrees, all divided by 1.46. That's going to equal the sine of angle 2. And we'll get a calculator out. All right, so we have, we'll clear all that. Okay, 25. Okay, the sine of 25 times 1.00029 divided by 1.46. That gives us, I should use the same color, 0.28955. It's going to equal the sine of theta 2. So theta 2 is going to equal the inverse sine of 0.28955. And we get 16.8 degrees. So our angle of refraction is 16.8 degrees, and that's consistent with what we expected and what we talked about in our conceptual ideas of refraction on a previous video. So good. All right, so utilizing Snell's law to get some more detail about how light rays are refracted going from one medium to another. Good job.